May 24th, 1883, Brooklyn, New York. The engineering reports from European bridge specialists would never fully capture what they witnessed that morning. American workers walking across a suspension bridge spanning 1,595 feet using methods that defied everything European engineering tradition said was mathematically possible. Through the river mist and construction noise of the East River, identical steel wire cables supported loads that seemed impossible to European observers. No iron chains, no stone foundations reaching bedrock, no Roman construction methods. Yet they carried 1,800 vehicles with stability that European bridges could not match. In European capitals, master engineers required centuries-old stone techniques to span major rivers. Each bridge was essentially custom masonry, different foundations, different materials, different structural approaches. Most carried weight limits far below what cities actually needed. The Americans were operating with engineering philosophy the Europeans had declared scientifically impossible: steel wire cables, pneumatic foundations, mathematical safety factors double European standards, load capacities that reduced construction time from decades to years while supporting unprecedented traffic. 3,000 miles from European workshops, the most decisive bridge-building revolution in engineering history was revealing itself, not in superior stone cutting, not in premium iron chains, but in the systematic wire-spinning techniques that connected every American cable strand in ways European chain-link traditions never imagined possible. The morning ferry from Brooklyn to Manhattan crawled through choppy East River waters, its paddle wheels churning against the December current of 1867. Among the 150,000 daily passengers crowded onto the deck, merchants clutched their coat collars against the salt spray while dock workers stamped their feet to maintain circulation. Every winter brought the same cruel arithmetic. When ice locked the river solid for weeks at a time, America's first and third largest cities became islands unto themselves. Commerce ground to a halt. Workers couldn't reach their jobs. Families remained separated by a mere half-mile of water that might as well have been an ocean. Standing at the ferry's bow, John Augustus Roebling pressed a leather portfolio against his chest and studied the river's treacherous currents with the calculating gaze of a 61-year-old engineer who had spent 3 decades defying conventional wisdom. The Prussian immigrant's weathered face bore the confidence of a man whose wire rope bridges in Pittsburgh and Cincinnati had already proven European methods obsolete, though none had attempted anything close to the span now demanded by the East River's width. 1,595 feet from shore to shore, 50% longer than any suspension bridge ever constructed. The technical challenges seemed insurmountable to every engineer except Roebling himself. The river's depth required foundations sunk deeper than any pneumatic caisson had ever descended. The salt air would corrode iron chains within decades, demanding a material solution no European bridge had ever tested at scale. Most daunting of all, the sheer distance required cables strong enough to support their own weight across an unprecedented span while carrying the heaviest traffic loads any bridge had ever been asked to bear. European engineering orthodoxy had crystallized around one immutable principle since the catastrophic collapse of England's Broughton Suspension Bridge in 1831, when 74 soldiers marching in synchronized step had created resonance vibrations that destroyed the 137-foot span in minutes. British and French engineers had concluded that suspension bridges over 1,000 feet were mathematically impossible. The cables would snap under their own weight long before reaching the far shore. Stone bridges built to Roman specifications remained the only proven method for major river crossings, regardless of cost or construction time. Yet Roebling's portfolio contained calculations that contradicted 3 decades of European engineering consensus. His secret lay not in iron chains, which every European suspension bridge employed, but in steel wire cables spun strand by strand directly in place above the river. Each cable would contain over 5,000 individual wires, each drawn to precise specifications in his own wire rope factory, each contributing to a distributed load system that European chain-link methods could never achieve. The mathematics were elegant in their simplicity. Thousands of small wires sharing the load created exponentially greater strength than massive iron links concentrated at specific stress points. The ferry's whistle shrieked as the vessel approached the Manhattan dock, where Roebling would present his proposal to the New York Bridge Company Board. Directors had already received dismissive correspondence from London's Institution of Civil Engineers, declaring that Herr Roebling's wire rope may suffice for his modest provincial spans, but the East River's salt environment will destroy such experimental materials within a decade. French engineering societies had published similar condemnations, noting that American engineers lacked the centuries of bridge-building experience that European methods represented. Roebling understood their skepticism came from professional self-preservation rather than scientific analysis. European engineers had built their reputations on masonry techniques, perfected by Roman legions, refined through medieval cathedral construction, and validated by centuries of successful river crossings. American methods threatened to render their expertise obsolete overnight, transforming bridge building from an art practiced by master craftsmen into a mathematical science accessible to any engineer capable of precise calculation. The docking procedure itself demonstrated the bridge's necessity with brutal clarity. As the ferry's crew threw lines to shore workers, passengers pressed toward the gangplank in a surge that threatened to overwhelm the vessel's stability. Winter ice frequently trapped ferries for days, stranding commuters and shutting down commerce between the two cities. A permanent crossing would transform regional economics by guaranteeing year-round transportation, but only if it could withstand the East River's notorious storms and ice flows that had destroyed previous attempts at fixed crossings. Walking down the gangplank with measured steps, Roebling carried blueprints that specified innovations no bridge had ever attempted: pneumatic caissons descending 78 feet to Manhattan bedrock, Gothic Revival towers rising 276 feet above the water, and 4 main cables each containing 14,000 miles of steel wire. The engineering challenges would require solutions that existed nowhere in European textbooks, demanding American innovation at every stage of construction. The morning's ferry ride had reinforced what Roebling already knew from 30 years of American engineering experience. European methods were designed for European problems. The East River demanded American solutions, bold, mathematical, and willing to risk failure in pursuit of revolutionary success. His wire rope bridges had already proven that calculated risk could triumph over conservative tradition, but the Brooklyn Bridge would test whether American engineering could build for centuries rather than decades. The betting money remained on failure, but Roebling's calculations suggested otherwise. The massive wooden caisson descended into the East River muck with mechanical precision, its airlocks hissing as compressed atmosphere maintained the underwater workspace where men carved foundations from living rock. Washington Roebling stood on the Brooklyn shore in March of 1870, watching steam pumps force 21 pounds of pressurized air per square inch into the sealed chamber, nearly twice the atmospheric pressure that human lungs were designed to process. The caisson itself represented engineering audacity that European methods had never contemplated. 168 feet long, 102 feet wide, descending 1 foot per week through boulders and quicksand toward bedrock that lay 45 feet beneath the river bottom. Inside the pressurized chamber, immigrant workers wielded pickaxes and shovels in stifling heat that reached 100 degrees Fahrenheit, their movements illuminated by calcium lights that cast eerie shadows against the wooden walls. The air itself felt thick enough to chew, saturated with moisture, and the metallic taste of compressed gases that made every breath a conscious effort. Workers carved granite blocks and hauled away debris in 16-hour shifts, their bodies adapting to atmospheric conditions that no human had ever experienced for extended periods. European engineering tradition demanded that bridge foundations reach bedrock or abandon construction entirely, a principle validated by centuries of stone bridge failures caused by inadequate foundations. Yet the Manhattan caisson faced a geological nightmare that threatened to destroy the entire project. As the chamber descended past 60 feet, then 70, bedrock remained tantalizingly out of reach. Drilling samples indicated solid foundation lay somewhere near 90 feet below the surface, requiring excavation through layers of hardpan clay, quicksand, and massive boulders that defied conventional removal techniques. The physical toll mounted with every foot of descent. Workers emerged from their shifts with nosebleeds and severe joint pain, symptoms that project doctors initially attributed to overexertion rather than the decompression sickness that was slowly crippling the workforce. Men complained of paralysis in their arms and legs, mysterious pains that struck without warning, and breathing difficulties that persisted for days after leaving the caisson. Several workers died from what became known as caisson disease, though no physician understood the medical mechanism behind their suffering. Washington Roebling himself descended into the chambers daily, monitoring excavation progress and maintaining the demanding schedule that kept construction moving forward. His military experience at Gettysburg had taught him that complex logistics required personal oversight. Theories meant nothing if execution failed in practice. Each descent into the pressurized environment exposed him to the same atmospheric conditions that were destroying his workforce, though his engineering focus prevented him from recognizing the cumulative damage occurring within his own nervous system. By late 1871, the Brooklyn caisson had reached solid ground, and construction crews were laying the massive granite blocks that would anchor the tower foundation. Success on the Brooklyn side validated Roebling's pneumatic excavation methods, proving that American innovation could solve problems that European orthodoxy declared impossible. Yet the Manhattan caisson presented challenges that threatened to vindicate every European prediction of American failure. At 78 feet below the river's surface, drilling samples from the Manhattan site revealed hardpan clay that would require months of additional excavation to reach actual bedrock. European engineers monitoring the project through newspaper reports gleefully predicted abandonment, noting that no pneumatic caisson had ever descended to such depths successfully. The atmospheric pressure required to maintain the workspace approached the limits of human endurance, while the excavation costs were consuming the project's contingency funds at an alarming rate. Washington Roebling faced the decision that would define American engineering's reputation for generations. European tradition demanded reaching bedrock regardless of cost or time requirements. Better to build slowly on proven foundations than risk catastrophic failure on inadequate support. American pragmatism suggested a different calculation. 30 feet of compressed hardpan sand could support 90,000 tons if the mathematics proved correct. The decision required trusting American engineering theory over European empirical tradition. Standing in his field office overlooking the Manhattan excavation site, Roebling reviewed load calculations that European engineers had never attempted. The tower's weight would distribute across the caisson's massive base, creating pressure per square foot that the hardpan layer could easily support according to soil mechanics principles. The safety margin exceeded anything European bridges demanded, yet the decision meant building on foundations that existed nowhere in European engineering manuals. The mathematical certainty drove Roebling's final decision in January of 1872. 30 feet of hard sand will hold 90,000 tons, he declared to the construction supervisors, authorizing crews to stop excavation and begin foundation work on the compressed hardpan layer. European engineering societies received the news with barely concealed satisfaction, predicting that the Manhattan Tower would settle into the river within decades, vindicating their warnings about American experimental methods. Yet, even as foundation work proceeded according to plan, the physical cost of the pneumatic excavation was destroying Roebling himself. Months of daily descents into pressurized chambers had saturated his nervous system with nitrogen bubbles that would not dissolve properly during decompression. In May of 1872, he collapsed from severe decompression sickness that left him partially paralyzed and unable to visit the construction site. The project that European engineers expected to fail from inadequate foundations now faced a more immediate crisis. The chief engineer could no longer physically direct the construction of his father's revolutionary bridge. The traveling wheels rolled across temporary cables stretching between the Brooklyn and Manhattan towers, their steel mechanisms carrying individual wires that would eventually form the bridge's main support system. Emily Warren Roebling stood on the Brooklyn anchorage in December of 1876, watching the wire-spinning operation that her bedridden husband could no longer supervise directly. Each main cable required 5,282 steel wires, each 1/8 inch thick, each 3,578 feet long. The mathematical precision demanded by the process left no margin for error, 14,000 miles of wire per cable, spun individually using traveling wheels that European engineers had dismissed as mechanically impossible at such scale. From his bedroom overlooking the construction site, Washington Roebling communicated engineering decisions through Emily, who had taught herself higher mathematics and cable construction theory during the months of his recovery from decompression sickness. The wire spinning process represented the most revolutionary aspect of his father's design, abandoning the iron chain construction that every European suspension bridge employed in favor of steel wire rope techniques that distributed load across thousands of individual strands. European critics maintained that salt air corrosion would destroy the steel within decades, while iron chains had proven their durability across centuries of bridge construction. The Bessemer steel wire arrived from the Roebling family factory in Trenton, each coil inspected according to specifications that exceeded any wire rope standards in existence. Tensile strength tests revealed the wire could withstand 160,000 pounds per square inch before breaking, strength that European iron chains could never achieve. Yet the wire's superiority meant nothing if Lloyd Hay, the contracted supplier, continued delivering inferior materials under cover of legitimate inspection certificates. Emily had discovered Hay's fraud through meticulous record-keeping that Washington's illness had forced her to maintain. Overnight deliveries of rejected wire replaced inspection-approved materials in systematic exchanges designed to escape detection by busy construction supervisors. 221 tons of substandard wire had already been spun into the cables before Emily's investigation revealed the extent of Hay's deception. European engineering societies would certainly use the scandal to vindicate their warnings about American experimental methods and inadequate quality control. The mathematical implications of the wire substitution demanded immediate calculation. Washington's original design specified a 6-to-1 safety factor, meaning the cables could support 6 times their intended load before approaching failure. Hay's inferior wire reduced the safety margin to 5-to-1, still stronger than any European bridge ever constructed, but below the engineering standards that John Roebling had insisted upon for his revolutionary design. European bridges typically operated with 3-to-1 safety factors, considering such margins adequate for proven construction methods. Rather than abandon months of cable construction work, Washington made the characteristically American decision to engineer around the problem through mathematical precision rather than starting over with traditional methods. His calculations from the bedroom demonstrated that adding 150 additional wires to each cable would restore the original safety margin while using Hay's superior wire as penalty payment for the fraud. European engineering orthodoxy would have demanded complete cable replacement, but American pragmatism suggested that superior mathematics could compensate for inferior materials. Emily supervised the penalty wire installation personally, ensuring that Hay's crews added the specified strands according to Washington's precise instructions. The additional wire increased each cable's diameter and weight, requiring structural calculations to verify that the towers and anchorages could support the modified loads. Every mathematical adjustment demanded verification against the original design specifications, transforming Emily into the project's de facto chief engineer while Washington remained physically incapacitated. By June of 1877, cable spinning commenced with steam-powered machinery that European engineers had never witnessed in suspension bridge construction. Master spinner E.F. Farrington supervised crews working on 4-foot-wide catwalks 135 feet above the East River, threading individual wires through pulleys with mechanical precision that reduced human error to negligible levels. Each wire required a complete round trip between anchorages, taking 10 minutes per crossing when weather conditions permitted safe operation. The scale of the wire spinning operation dwarfed any construction project in American engineering history. 18,744 individual trips were required for each main cable, with 4 cables demanding over 74,000 crossings total. European chain link construction could complete similar spans in months rather than years, but Roebling's distributed load system promised strength and durability that iron chains could never achieve. The mathematical theory remained unproven at such scale, making every wire crossing an experiment in structural engineering. Working through autumn and winter weather that frequently halted operations, Farrington's crews maintained the demanding pace that kept construction moving toward completion. Ice storms coated the wires with frozen precipitation that added dangerous weight to the temporary cables, while high winds created oscillations that threatened to shake workers from the narrow catwalks. European engineers monitoring the project through newspaper reports noted that such weather delays proved their criticism correct. American experimental methods created unnecessary risks that traditional construction avoided. Yet by October of 1878, the cable spinning was complete. 4 main cables, each 15 3/4 inches in diameter, stretched between the massive anchorages with mathematical precision that vindicated every calculation in Washington Roebling's original specifications. The cables were wrapped with iron wire and painted with protective coatings designed to prevent the salt air corrosion that European critics had predicted. The towers had held under the cable tension, the anchorages had held under the distributed loads. The wire substitution scandal had been resolved through American engineering rather than European tradition. The moment of ultimate testing would come when those steel wire experiments supported the actual weight of roadway construction and daily traffic loads. Master rigger E.F. Farrington secured himself into the boatswain's chair with methodical precision on the morning of August 25, 1876, preparing to become the first human being to cross the East River, suspended from John Roebling's experimental wire cable. The temporary footbridge cable stretched 1,595 feet between the completed Gothic towers, its steel wire construction representing engineering theory that European bridge builders had never tested at such unprecedented scale. Crowds gathered on both Brooklyn and Manhattan shores to witness either the vindication of American innovation or the spectacular failure that European engineering societies had confidently predicted. The chair's pulley system engaged with the wire rope as Farrington pushed off from the Brooklyn Tower, his weight creating the first meaningful test of the cable's load-bearing capacity under dynamic conditions. 22 minutes later, he stepped onto the Manhattan Tower platform as cheers erupted from spectators who had witnessed the crazy American wire carry a human being across one of the world's most challenging river crossings. The successful transit proved that Roebling's distributed load theory functioned in practice, not merely in mathematical calculations performed from a sickbed. Washington Roebling watched the crossing through field glasses from his Brooklyn Heights bedroom, his paralyzed condition preventing direct participation in the triumph that validated his father's revolutionary engineering principles. Emily stood beside him, recording technical observations that would guide the next phase of construction, suspending the actual roadway from cables that had now proven their ability to support concentrated loads safely. The moment marked a psychological breakthrough for the entire project. European skepticism would be harder to maintain when American methods produced visible success. Spring of 1879 brought Washington's decision to employ steel throughout the entire deck structure, abandoning the stone and iron construction that European bridges required in favor of materials that American industry had perfected during the Civil War. The Brooklyn Bridge would become the world's first all-steel suspension bridge. Steel cables, steel suspenders, steel trusses, even steel floor beams. European engineers condemned this wholesale adoption of untested American materials, noting that iron had served bridge construction reliably for centuries, while steel remained experimental for major structural applications. The steel truss sections arrived from Pennsylvania foundries according to specifications that prioritized strength-to-weight ratios over the massive redundancy that European stone bridges employed. Each truss member was precisely calculated to carry its designated load with minimal excess material, creating a deck structure that weighed significantly less than comparable European designs, while providing superior load distribution across the supporting cables. The mathematical precision required for such construction exceeded anything attempted in 19th century engineering, demanding manufacturing tolerances that American industry had developed for artillery production. Installation of the floor trusses proceeded through 1880 and 1881 with mechanical precision that European observers grudgingly admired. each steel section locked into position according to engineering drawings that Emily had helped refine during Washington's convalescence, creating a unified structure that distributed traffic loads across thousands of individual connection points. The deck's flexibility under wind loads concerned European critics, who preferred the rigid stone construction that had withstood centuries of weather without visible movement. Yet the bridge's designed flexibility represented advanced understanding of dynamic loads that European engineering had never systematically studied. Washington's calculations anticipated wind forces, thermal expansion, and traffic vibrations that would destroy rigid structures, incorporating controlled movement into the design rather than fighting natural forces with brute mass. The deck could flex up to 9 feet at center span under maximum load while maintaining structural integrity, a characteristic that European engineers viewed as dangerous instability rather than sophisticated engineering. By October of 1878, the cable spinning was complete and wrapped with protective iron wire that gleamed in the autumn sunlight. Each main cable measured 15 3/4 inches in diameter, containing the 14,000 miles of steel wire that represented the largest wire rope construction project in world history. The cables supported their own weight across the unprecedented span without visible sag, vindicating every mathematical prediction that Washington had made from his bedroom calculations. European engineering societies maintained official skepticism, but their technical journals began publishing detailed analyses of American wire rope techniques. The installation of stay cables during 1881 provided additional structural support that European suspension bridges had never employed. These diagonal cables connected the deck directly to the towers, creating a hybrid design that combined suspension bridge efficiency with cable-stayed bridge stability. The innovation represented purely American engineering thinking. European tradition preferred single, structural systems rather than hybrid approaches that complicated construction while improving performance. Testing the completed structure required gradual load increases that would reveal any weaknesses in the revolutionary design. Washington specified that construction materials be distributed across the deck in patterns that simulated maximum traffic loads, creating stress patterns that the untested steel wire cables had never experienced. Each test load demonstrated that the bridge's deflection matched his mathematical predictions precisely. 9 feet of sag at center span under 14,700 tons of dead weight. The moment of ultimate vindication arrived as construction crews completed the final deck sections in early 1882. The Brooklyn Bridge carried its own massive weight exactly as John Roebling's original calculations had predicted 15 years earlier. The tower showed no signs of settling into their controversial hardpan foundations. The anchorages held firm under cable tensions that exceeded any loads in European bridge construction. The wire substitution scandal had been resolved through mathematical precision rather than reconstruction. Most remarkably, the steel wire cables showed no signs of the salt air corrosion that European critics had confidently predicted would destroy the experimental materials within a decade. Standing on the completed deck structure, Emily Roebling could see both shores of the East River connected by engineering that existed nowhere else in the world. The bridge awaited only the installation of approach ramps and roadway surfaces before opening to the traffic that would provide the ultimate test of American innovation versus European orthodoxy. President Chester Arthur stepped onto the Brooklyn Bridge deck at precisely noon on May 24, 1883, accompanied by the mayors of New York and Brooklyn and a procession of carriages that would test 15 years of American engineering theory against the skepticism of an entire continent. Emily Warren Roebling led the ceremonial convoy, carrying a live rooster as a symbol of victory, while 150,300 people crossed the span on its opening day. The bridge carried 1,800 vehicles without registering so much as a tremor in the steel wire cables that European engineers had predicted would fail under far lighter loads. The opening day triumph silenced the most vocal European critics, but skeptics remained convinced that time would vindicate their warnings about American experimental methods. Salt air corrosion would destroy the steel wire within decades, they maintained, while the revolutionary pneumatic foundations would settle into the East River bottom once heavy traffic began crossing regularly. European engineering journals published cautious congratulations while noting that true structural success could only be measured across generations of continuism. Service. P.T. Barnum provided the definitive proof of the bridge's strength on May 17, 1884, leading 21 elephants across the span to dispel panic rumors that had circulated after a crowd stampede killed 12 pedestrians the previous Memorial Day. Jumbo, the famous circus elephant, led the procession across cables that registered no deflection whatsoever under the unprecedented load. The spectacle drew international attention to American engineering methods that could support circus elephants where European bridges struggled with ordinary carriage traffic. Washington Roebling watched Barnum's elephant parade from his Brooklyn Heights bedroom, his physical condition still preventing direct participation in the bridge that had consumed 17 years of his family's engineering legacy. The successful elephant test validated every calculation his father had made in 1867, proving that American wire rope construction could exceed European chain link bridges by margins that made direct comparison almost meaningless. European engineering societies fell into conspicuous silence, their technical journals ceasing publication of critical analyses that events had rendered obsolete. The bridge's daily traffic loads quickly exceeded every projection that 19th century planners had considered reasonable. Within months of opening, 30,000 vehicles crossed daily alongside 50,000 pedestrians, who paid the 1-cent toll to walk across what newspapers proclaimed the eighth wonder of the world. The steel wire cables absorbed these loads with mechanical precision that demonstrated the superiority of distributed load systems over the concentrated stress points that European iron chains created. Yet the bridge's ultimate vindication would emerge not from its opening day success, but from its performance across decades of service that no 19th century engineer could have imagined. By the 1920s, automobile traffic had replaced horse-drawn carriages with vehicles that weighed significantly more than original design specifications anticipated. The cable system adapted to increased loads without visible strain, proving that John Roebling's 6-to-1 safety factor had been conservative rather than excessive. The Great Depression brought subway construction that added rail traffic to the bridge's load requirements, creating dynamic stresses that Victorian engineering had never contemplated. Twin rail lines carrying fully loaded subway cars crossed the lower deck, while automobile traffic filled the upper roadway, generating combined loads that approached the theoretical limits of European engineering design. The Brooklyn Bridge absorbed these stresses, while European bridges of similar vintage required major reconstruction to handle 20th century traffic demands. World War II demonstrated the bridge's strategic value as the only East River crossing capable of supporting heavy military equipment without load restrictions. Sherman tanks and artillery pieces crossed the span alongside civilian traffic, creating temporary load concentrations that would have destroyed bridges built to European specifications. The steel wire cables showed no signs of fatigue after 60 years of service that had subjected them to every conceivable stress test except the salt air corrosion that European critics had confidently predicted. By the 1960s, traffic engineers recorded 103,000 vehicles crossing daily alongside 30,000 pedestrians and 5,000 cyclists, creating total daily loads, equivalent to 57,000 tons in constant motion. Modern bridges required complete cable replacement after 50 years of such service, yet the Brooklyn Bridge's original 1878 cables continued performing flawlessly with minimal maintenance beyond periodic painting and wire wrapping replacement. The stunning comparison with later suspension bridges revealed the superiority of Roebling's over-engineering philosophy. The Golden Gate Bridge, completed in 1937 using modern construction techniques and computer-optimized materials, required major cable inspection every 2 years with complete cable replacement estimated at 50 to 75-year intervals. The Williamsburg Bridge, opened just 20 years after the Brooklyn Bridge, consumed $1 billion in cable repairs during the late 20th century. The Manhattan Bridge required $900 million in cable maintenance to address fatigue problems that the Brooklyn Bridge had never experienced. The secret of the Brooklyn Bridge's extraordinary longevity lay in John Roebling's steel wire drawing process, which created high-carbon steel with tensile strength of 160,000 pounds per square inch. Modern cables used higher-strength steel rated at 225,000 pounds per square inch, but lacked the fatigue resistance that Roebling's manufacturing techniques had inadvertently created. The pneumatic spinning technique distributed loads across thousands of individual wires, rather than concentrating stress in massive cable sections that modern bridges employed. Most crucially, Roebling's 6-to-1 safety factor provided margins that modern computer optimization had eliminated in favor of cost efficiency. Contemporary bridges operated with 3-to-1 safety factors that reduced construction costs while creating planned obsolescence requirements that Roebling's Victorian over-engineering had avoided entirely. The Brooklyn Bridge continued carrying 21st century traffic loads on 19th century cables that had outlasted 3 generations of supposedly superior replacement bridges. Standing at sunset in 2024, traffic streams across cables spun 146 years earlier by workers who could never have imagined the loads their craftsmanship would eventually support. John Roebling's impossible bridge had not merely connected Brooklyn and Manhattan, it had proven that American engineering could build for centuries rather than decades, creating infrastructure that outlasted the European methods it had originally challenged.